And welcome to our stream, or my stream today. Interestingly, my remote control for Streamlabs doesn't work that well, so I will just try to log into YouTube on my phone real quick. Give me a second. You need to go follow Valzu Gamer. Also, hello Johnny. Thanks, Masi Kalinowski for subscribing. All right. Maybe this works now. So give me one more second. Maybe the remote works now. No. Maybe if I exit studio mode. Yeah, then it will probably work. So welcome to the stream once again. So today I will step back from the Nanoleaf project a little bit, and I will be fixing one of the PCBs I made for my girlfriend for what was that again, for her birthday? or for Christmas? Christmas, yeah, it was a Christmas present. So the issue with this PCB is that the micro USB port ripped right off, so I need to fix that and maybe put on a new one, or I will just drill through the PCB and zip tie it on. But let's have a look at the PCB first. So if I do this now, then it works. Yeah. So also one thing is missing. I need to see the camera. Yeah. So this is the PCB I made for my girlfriend. Let's zoom out a little bit. It's a heart which makes some animations. I never showed this project anywhere. So on here are 74 LEDs. These are the APA ones, which are individually addressable. And then on the back, we can find an ESP8266 and a voltage regulator, and then a 5-volt USB input on this side. The stand for the heart is just some little PCB or socket strips. And the interesting thing is that the right socket strip is used for programming the ESP, so I can just plug in a programmer directly in here, and then I'm able to program the ESP, which is really nice. So the USB port is only used for powering stuff, and that is what ripped off. Here's the USB cable that was attached to it, so the thing is still attached to the cable, which I can get off. So we might need to think of a way of either getting one of these back on, but it seems like the track has been ripped off. So I will first turn on my soldering iron. Would be a good idea. Make some space on my desk. Also for you, Johnny, you will be probably interested in that. Since I fixed the issue with the Nanoleaf clone yesterday, today I tried the maximum baud rate at which the ESP will be able, or not the baud rate, the byte rate at which the ESP will be able to send data. And if I only set a static collar, I'm getting about 80,000 bytes per second, which is only 80% of the theoretical maximum, which is good. But if I use the plasma animation, which uses more sine waves and cosine waves, then it goes down to 8,000 bytes per second. So there's still some room of improvement. Also, doubling the clock of the ESP to 160 megahertz also doubles the speed. So with the plasma, we can then get 14, 15 thousand bytes per second, but it's not a lot. If you recalculate to the 60 FPS and such, then you can also only control like 15 tiles. So what I want to do now first is to clean up the PCB a little bit. Where is my stuff? Alright, I need to get some things. Loads of float calculations. Yes, we are using loads of float calculation, and that's why we are probably going to be using a fixed point integer implementation to get rid of that issue, and then also use the hardly optimized functions of fast LED for all the other functions we are using, like for example the cosine and sine, and that should fix the issue hopefully. So here I have some how do you call that, like this braided copper wire. Yeah, solder wick is the name. So let's wick up some of the solder on the board. Probably use some higher temps for that. That is how we solved it on the C64, but that was only 1 megahertz. Yeah, so the ESP has, depending on the mode you set it to, or the ESP8266 has either what was it, 80 megahertz or 160? This doesn't work that well. Maybe we will need some flux. Only have this pretty fluid stuff. Yeah, that works a lot better. So sorry. All right, so we need to restore the 5 volt and ground wire. So if I can focus on that, you can see that the 5-volt rail is almost gone because this rail right there is one of the USB pins, and that on the right is actually the ground pin, so we can still probably use that. I will throw away this micro USB one, or the micro USB connector. I have a new one right here, so let's get that. And then if we fix this, we can give it a little test run and then maybe do some stuff for the triangles. We also tested the maximum baud rate which the triangles can handle, so which is 40,000 bytes per second, around something like that. Because if you send more bytes than that, then the LEDs will just start to flicker because that's a little bit too fast. So let's see if we can just fix it by putting on a new one. We might be able to do that if we scratch off some of the board. To give us the bare copper. Sorry if you can't see anything, but I need to see something to be able to scratch off the code of the PCB. So there we have some bare copper. Right there. So now we have some bare copper to work with. So let's throw on the USB thing again. Since we don't need the center pins, I will just carefully remove them. Because ground should be on one end and VCC on the other. So let's focus. So let's try to get rid of these. So 2 of them are gone. I don't know if you can see anything. Yeah, so we are only left with 2 of the pins, like that. And now we can try solder that back on and then give more care to soldering on the tabs of the micro USB port, so it will sit there tighter and not come off again. Let's solder it on first. I'm wondering how I'm going to do that. So this camera is not focusing. Weird. Because I can't touch it while soldering, can I just... Oh yeah, that works. Okay, let's add some flux, which I didn't do before. You need to be careful with these USB ports because you can get the solder into the jack itself and then it won't work anymore because you can't get a USB cable in. But I think this should hold better right now. So there's some solder on the side going across the whole tab. The other side will be a little bit more tricky because there's this stand. But yeah, I just removed the plastic of that. And that should give us room to solder on the other side. Maybe let's also add some more flux again, because that helped a little. All USB connectors suck when it comes to soldering. Yeah. So the other side also looks far better now. Let's do a quick test before we solder on the other parts. Oh, I think I broke the USB connector. Yeah, I can't get the USB cable in because there's solder inside the connector. Nice. So that's why I didn't solder on the wires yet. So the connector has to go again, and then we will use another one to try again. So I think we should be able to remove it by just heating up the connector itself, if the camera would focus. Let's try a different mode. Hey. Oh, this one works. Oopsie, yes. So this comes off. We will need to clean it again with some wick. The wick is not working so well. Well, this looks awful. Give me 1 second and I will get some isopropyl Q-tips, which Big Clive showed in one of his videos. If I can find those. Are they even here? Oh, I really don't know where they are. No, I put them somewhere. Okay. Oh, there they are. Found them. Alright. I'm back. So, I don't know if you know these, but these are Q-tips, which look like this. Maybe let's show it here. And in the middle, as you can see, they're filled with isopropyl alcohol. So if I break off the marked end, or is this the other one? No. The other side, the other tip, will fill with the isopropyl alcohol, and then I can just clean up the PCB with it. Yeah, we'll probably need to give it a proper cleaning. But this can then go into the trash, and everything is nice and clean. So here goes attempt number 2. Hopefully I have enough of these micro USB connectors, because that's the last one I found in these things. Oh yeah, we need to break off the middle pins again. Alright, that's them gone. Let's see. I think we need to clean it up some more. There's still some solder left. So what I will do is put on some of the flux on the wick, and this tends to work a lot better for me. Yeah. So now we have a far smoother surface to get this on again. So here goes attempt number 2. All right. Okay, this time I think it worked. Yes. So the tap is soldered incorrectly, but the USB port is still open. Now the other side. this is a little bit more tricky. So I think this time it is properly soldered on. And let's try plugging in the USB cable, which works. But as you can see, the USB port is still flexing a little bit. Because it is not held on from the bottom, because obviously I can't SMD solder it. I don't have any solder paste. So let's try giving it a little bit more flux and more solder. So hopefully it will seep in. See if that has done anything. No, still pretty loose. Right. Let's try it another time, but putting solder underneath the USB port first. Because third time's the charm? Yeah, third time's the charm. Right, you are gone. Yeah, so we need to clean it up again. But this time only the sides. I think we can reuse the old USB. We can try. So I'm trying now to put on some solder on the bottom of the USB port, which worked great. Just so it is pre-tint a little bit. Probably cooled off now. So now we need to align it and then clamp it down. Oh, this is so tricky. And then hope that heat will do the rest. Okay, that's not working. So have we managed to solder in the base of it? I think so. Oh no, it just came off again. Oh, this is not working as intended. Right, let's spread out the solder on the bottom. And then try placing it again. Ah, this is frustrating. You need to heat it up enough that the bottom solder will melt and I'm able to solder it on from the bottom. Might be able to do that when I'm heating up one of the sides here on the right, this one there. And still, if this won't work, we can still just solder on the cable directly. Need some hot air. Well, I think you think we can fix it with hot air? Then we can still try using my hot air thing. So, which will probably make a lot of noise. Right. So, what temperature do you recommend, Johnny? And do you recommend using a nozzle? Something like this? Is your girlfriend's heart broken? Yes. She ripped off the USB port and now it doesn't work anymore. So 100 degrees. Let's crank you up to 380. Smells nice. Hopefully this thing won't combust on me. Alright, so the pins are melting. So let's get them out. Oh, and my thingy is melting also. So hot air it is. Why are you not coming out? Alright, let's fix that with the soldering iron. Turn 80 degrees instead. Turn 80 degrees. Yeah, let's clean this up once more. Alright. Should melt at 200 degrees. Well, this solder right here is unleaded, but I don't know if I used leaded solder or not. So let's get my thing ready. Alright, so this is melting. So let's get our USB. Right, so this has worked astonishing well. Now we need to wait for this to cool off. Hopefully we didn't break anything. Easy peasy. I should probably use my hot air soldering station more. Oh no, it's not a hot air soldering station, but my hot air thingy. Oh, we can also use it to cool. Oh! We need to do it again. Oh no, see what happened. There's solder inside the USB port. Time to remove it again. But at least this time we know how to do it, or at least I know how to do it. And there's the USB port gone. So let's add some solder for the next port. And clean it up once more. Well, I'm getting really good at it now. I guess this is the first time I pretty much soldered anything with hot air. So also get some of the rest of the PCB. Practice makes perfect, yes. But now you have to watch me fail like 100 times. Do I have another one of these USB ports? If I don't, then I will cry. Oh. Oh, where do I have more of those? Do I have more of those? Or were these the last two? Oh, I remember. Wi-Fi enabled hard, yes. I hope you have secured it against remote exploration. Well, it can't be explored, I guess. So I thought I had some of these in my thingy here. But it looks like I cleaned them all out of there. I have male USB things. Oh no. Oh, I know I have them somewhere. What do we have here? Those are switches. More of the APA 106, which I used for the project. Nope. Oh, maybe this. No, these are battery connectors. Linear potentiometers. Transistors. PCBs, wireless stuff, Arduinos, broken Arduinos. Oh wow, I don't have anything there. Gotta go, friend just arrived. Bye, Johnny. Have fun. Is there anything I can use in here? No. Oh, maybe there's some in here. Oh, these are flat flex connectors. Oh, maybe, oh yeah, I remember now where they could be. I have this box with random assorted parts. Alright. So these are 12-volt barrel jacks, coils, LEDs, integrated circuits, charging boards, board-to-board connectors, female USB-A. No, this can't be true that those were the last micro USBs I had. Oh no. I promised that I would fix the heart until the weekend. That will be bad if I can't deliver it. What's in here? No. Alright, we have some boxes left to check. Probably nothing in here because this is a box full of PCBs. JST connectors. Maybe also you. Oh, there they are. Oh, there are a few of them. Yeah, nice. So here I have some more of them. And there's already one jumping at me. So there is the new micro USB thing there. So this time let's heat up the board again. All right. The desk changed its color a little bit. Oh, this PCB is hot. Let's see if we can recover the desk at least. No, I think it will be brown forever now. Probably need some fireproof stuff next. Let's clean the PCB once more. And on the back as well. Henrik, oh no, you have left a black mark on your girlfriend's heart. Well, isopropyl alcohol will fix that issue. Just use alcohol. Alcohol fixes things. No, it doesn't. Don't listen to me. So... Oh! No, I forgot to remove the pins first, but it will be fine. We now just need to give it a little tap with the soldering iron and connect the 5-volt and ground pin. Oh, I bridged the pins. No. Flux, help me. See, that's why I wanted to remove the pins in the first place. All right, it's time to do a little continuity testing. So, ground should be on here and not connected to VCC, and the pin next to VCC should not be connected to the other one, so that works. Let's see if the USB port is a little bit stronger now. Yeah, it's still makes funny noises, but I also want to touch up on the one side a little bit. All right, Let's see if it works again. I need a power bank of some sort. So everyone is excited now to see what will happen. So that worked. So on startup it says I love you. And then let's wait. Now it says connected, so it has connected to the Wi-Fi. And then if we press the wrong button. So let's wait for that again. Probably should have put one of the buttons on the back side. Takes some time. Connected. And then if we press the lower button, the heart will tell us how long I'm together with my girlfriend. Oh. What are you saying? Oh, it said something was invalid. Hey, it's almost Feb 14 project. Valide. Okay, something is obviously not working correctly. Oh, maybe because the power bank shut off. I might need to fix some bugs in the software again. Right, so let's be quick. So if it says connected, it should technically have the current time. Hey, why is it not working? Maybe let's use the PC as a power supply. Bolukan just printing out everything that the heart says. So, oh yeah, now it has the time because the lights will dim if it is evening. So if I press it, why you no work? 2 years, 5 months, and 3 days. And then you see this heart animation. If I dim the lights, you can see that it will do this animation. And then it will go back to sleep. And then it has some secret features. So let's try that again. You press the button. Oh, why is the camera so interesting? I will restart the camera for a short second. Something wrong with the camera. Why is the frame rate so low? Maybe it's dark and then it doesn't like it. So 2 years, 5 months, 3 days. Oh no, it says it twice because I pressed twice. Night vision. Yeah, and then it does the heart animation. And for Christmas, it does. It shows the calendar, which counts down from, which counts down to Christmas Day, or what you would ever call it, and it shows the date and such, and some special things on Christmas. Lower frequency to get the needed ISO. Oh yeah, I get you. Cameras are not my thing. But programming is. Well, probably I should not put the power bank filled with lithium-ion batteries on top of the hot air station. So yeah, the heart is fixed now. We need to fix one more thing. And that is the pin headers that are removed. So let's get a new one. So we need 4. 4. Oh no, 4 socket strips. That's the correct terminology. Do I have another 4 one? Yes. Oh no, this one only has 3. Do I need to cut one? Or do I have... matching one? Nope, looks like we need to cut one. So we need 4. 1, 2, 3, 4, and then I will cut off the 5th one. And then we need my sucky thingy. And you know the procedure, I guess. And after that we will give it a little cleanup. And then I will be able to show you some of the progress on the tile thing. Okay, this didn't work. Probably need some solder on the soldering iron. That worked. That did not work. Ah, come on. That worked. That worked. That did not work. No, it's fine if one didn't work. We can still push it in. Well, this is not the right one. So let's apply some heat so I can get it in. And then we will solder it in, clean it up, and then call it done. So now it will stand upright again. Probably needs some tuning. Yeah, that's better. And then I will get some of my cleaning Q-tips, of which I have a lot. And then start cleaning the heart. Does acetone also work for this, or should it only be isopropyl alcohol? Because the acetone might destroy the PCB, I guess, maybe? Okay, these strings of stuff are bad. Oh, they're getting all over. So that goes into the trash. I guess at least the front needs to look nice. So let's get one more of these things. So you break off the one end and then the other end fills with isopropanol or isopropyl alcohol. Oh no, it's so clean that it squeaks. So Bolokan or Henrik, what are you doing this evening, or anyone else who's watching the stream? Because most people are doing something else besides. Working on your, Bolokan, are you working on your hexagon clock project? Alright, so I would say that this is fixed, and also a miracle that say that it is a miracle that I could fix it. I did yesterday, I programmed the getting my head cleaned after working today. Yesterday I programmed the coordinates of the ground plane. Oh yeah. So the ground plane, I would consider the coordinates of that being a little bit easier than all the tracks between the LEDs, but I don't know. So let's check once more if it still works after cleaning. So let's carefully plug in the USB cable. Yeah, the LEDs blink. I love you. I needed to learn how the object was organized. I'm learning the object of KiCad. And just it is just 6 XY coordinates. I agree that part. Yeah. So let's press the button and wait. Technically this should be... Oh, I didn't press quick enough. So it works. Yay. But your opinion about the size of a 5-volt track? For what? You are using a 5-volt track. I would use a 5-volt plane. Just make one side of the PCB a 5-volt plane and one side. Yeah, so 5.76 amps at 5 volts. There are charts online which can tell you. I will show you in a second. So this is considered done. I will set it aside so it doesn't break again. And I will also bring back the other project I'm working on and put it here. So this is the tile prototype, the ESP right here. So this needs to plug into the ESP, and it will then start its stuff and magic and just work. Then I also need to plug into Johnny Bergdahl's little programmer he gave me, which is working great. So far. So let's leave that aside and use a wire for each RGB. Give me 1 second. Need to clean up some stuff. And I will also need to take the face cam with me. So let's do this real quick. I thought of adding the pads for 96 condensators, but not populate them. But with 2 planes, I will not need them. Why? Because the planes make a huge capacitor. Well, the capacitance is not that large, I would think. Alright, so one more second. I need to turn on my light. So desk, right screen with bottom face cam. That's what we want. Also a face cam that's a little bit more like that. Yeah, that's better. So, Bolu Khan. I thought I had a mark for that. Right, so the German word for it is Strombelastbarkeit of Leiterbahn. And I had, yes, so one part of it will be the thickness of your copper layer, and then you have the maximum amperage depending on the temperature increase. So the standard JLC PCB will be 35 micrometers, I think. But let me check real quick. You can just do quote now. And then 1 ounce should be a little more. 1 ounce should technically be 35 micrometers. I think it also shows right here. Maybe not. 0.0347 millimeters. So yeah, that's pretty much 35 micrometers. And then what are you using for your so you want 5.76 amps to pass through. So I would suggest using a 4 millimeter wide track for that. So you have 6 amps with a temperature increase of 10 Kelvin. So if you have the 6 amps running through that track, it will get 10 degrees or 10 Kelvin hotter than ambient, I think. That's what is meant with that. So yeah, but if you think that 20 degrees are fine or 20 Kelvin, then you could also go to 3 millimeters. That's why I said using the whole layer as 3.3 volt and making, or 5 volt, and making sure that you have enough clearance so the current can pass through. No, the whole track needs to be 4 millimeters wide at every given position. So in each direction 4 millimeters. 576 is a theoretic maximum, of course. Yeah, because 4 millimeters is very wide. But if you just fill... I mean, we can look at the hard thing I made. I've used the same technique there. Where did I put it? Software, KiCad, no, it's not there. PCB, open that. So this is the PCB. Do I not have planes? Interesting. Looks like that there's something missing here because there's no planes and there are no connections between the LEDs. But yeah, if you look at it this way, then if these are your LEDs and for example, the output, oh no, it worked. It was a visual glitch, I guess. So I have it hooked up like this, so well, Command B, oh no, yeah, Command B turns it off, yeah, B fills it again. So if you look at this, then there's always a path going vertical. So there's always a path going vertical through each and every LED, so the current gets spread across everything. So if we have the 5 volts coming in from the back, can I see the bottom layer? Something is off. Oh yeah, now. All right, so now it's working. So the 5 volts coming from the USB for me just go to this LED right here, and then it just gets distributed throughout the PCB from the front layer. Maybe this track needs to be larger, but for this small amount of LEDs it's just fine. But as you can see, the backside is a ground plane, and then all the LEDs ground pins are connected to each other. And on the front, the VCC is just connected through everything. So that's the way I would do it. But then you need to make sure that the connections between the LEDs for the data in and output need to be oriented the same way, so only horizontal connections, so current can flow between, because if you do a vertical connection anywhere, then you cut off the plane going horizontally. In this case it's fine because the LEDs are oriented that way that the edges only connect, so there's enough ground plane to go around. And for these upper ones, there's enough going through the multiple LEDs. I use 50/50s and you have flow underneath. Yeah, so these are through-hole LEDs and you have SMD LEDs, so you might need to think of it differently then. So you might either need to do a wire for each LED. Oh yeah, between the pads there's room. Yeah, but you need to think of a way to connect it with the method I've shown before, like with the 4mm track width. I don't know if you will be able to fit that even on there, because 4mm is pretty wide. 4mm, like I have this ruler right here and the biggest track on there is 40 mil. Well, you technically can, well, where the power is coming from needs to be at least 4mm, and then from there to the last LED the track could get smaller. Yeah. Yeah, you are correct. Only where 6 amps flows. So at the end where I have something like 6 milliamps, 60 milliamps. No, wait. Yeah, it can be less. Yes, you're totally correct. But then you can always only power it from one side. For the tiles that I made, you can power them from any direction. So for the tiles I'm currently working on, I need to reset the ESP maybe? Yes. So it does its thing over there. Would you use wires for each LED? Well, it doesn't cost you anything more to use wires, so then yeah, you could use a wire for each LED. Doesn't matter, because the PCB will cost, or for each 4. It doesn't really matter. As I said, you could do the back plane all VCC and then have a wire connection for each individual LED. I mean, the production won't cost any more. But that's just my opinion, I guess. So let me upload the code for the ESP. For that I need to remove this thing right there. And then I can show you the latest point where we are at. So now the ESP is doing its animation. Because of the aesthetic reasons. Not use, well, you won't probably see the through-hole connections. Oh, no, not through-hole connections, the wires. You could hide them behind the LED. And then you won't see it at all. I guess you should have enough space for that. So, if we now look at the real term, we can see that we are currently only outputting 14,000 characters per second, which is bad. So that's where I'm currently working on. Okay, thanks, a lot more options now. Yeah, there are a lot more options. But as I said, everything you do on the PCB, like through-hole connections or vias or any parts put on there, won't cost any more to have more. So if you have a board with 20 vias and the same size as a board with 100 vias, I don't think that JLPCB will charge you more for that. Oh, I also forgot, as I said, my neighbors had the package with the LEDs. So give me a second. Here is the reel of 1000 WS2815. Yes. So these smell nice. And there are the LEDs. I will put them back into their moisture tight package if I would ever consider hot air soldering these LEDs, but I will probably just hand solder them. And then the new prototypes have been shipped. So ETA is currently, 12 volt LEDs, yes, to reduce the current and to have more LEDs. So I also bought 20 more LEDs, and that turns out to be the exact number of LEDs you would need. So if you have, not 2000, if you have 1020 LEDs and divide that by 6 LEDs per triangle, you come up with 170 triangles, which is pretty nice. So if I would take 170 triangles and all connect them in a line, then that would lead me to a line of triangles with the length of 170 times 0.07, because so I would have 11.9 meters of tiles, which is a lot. So to fill a whole wall, let's calculate how many tiles I would need to fill my whole wall. So I'll use that wall that you can't see. Body 2 times I minus 1 times 6 triangles for I count from mid to side. 2 times I minus 1 times 6 triangles. What is that? Almost good. Have to get my formula. So if I would want to fill up this wall right here, sadly you can't see that. So this wall is around 2 meters 60 by, let's see, 2 meters 60 by 2 meters 40. So let's write that down. Around 2 meters 60 by, what did I say? 2 meters 40. Almost 2 meters 43 something. So no, that's not what I wanted to show. No, that's no, with bottom face cam. So if we look at the online triangle calculator, one of our tiles is 140 centimeters by 140 by 14 by 14 by 14 centimeters. I to the power of 2 times 6. Remove that angle. So we need to divide our wall height by the height here. So in y direction, I design a hexagon with I equals 496 triangles. Ah. So what does the 4 stand for? 4 centimeters? No. No, 4 centimeters is not right. 4 meters. So we need to divide my room height, which is 243. 2 meters 43 divided by 0.4 is the size between mid and side, so 8 in a line. 8 LEDs in one line. So 2.43 divided by 13 equals 1024 triangles. All right, so 0.1212436. So we need 20 triangles in y direction, and then for the width, which is 2 meters 60, and we need to divide that by the half of the length. Oh wait, yeah, half of the length. So divided by 0.07. So I need 20 times 37 triangles. So to fill a whole wall, I would need 740 triangles. But I use 1 LED per triangle. Ah, okay, now I get it. I'm using 6 LEDs per triangle. So 740 triangles to fill a whole wall. That's a lot of triangles. And also I would need to have 2 controllers controlling them. So divide that by 2. Yeah, I would need 3 controllers to control them, because I can only control 254. That's far more than 1000 LEDs. Yeah, that would be 740 times 6, 4440 LEDs. And 3 controllers working in unison, which will be hard. So one thing that I implemented for the LED animations is this RGB plasma animation. But I was also thinking about implementing or writing a sync, or like an endpoint for color chord. So I could use color chord and have the tiles animated by CNLaw's awesome color chord. I also already got that to work. So all I need to do for that is just start the exe in here. Where is it? There. And then if I would have sound on my PC, which I currently don't, then it would do some animation. Maximum 266.4 amperes. Realistic? For what? 1000 LEDs or for 4400 or whatever? All right, let's switch to this. Is it 60 milliamps? I thought it would be less for the 12 volt variant. WS 2815. This is the topic. Yeah, so the WS 2815 only uses 15 milliamperes max. So 180 milliwatts. So for the maximum I could build right now, which would be this amount of LEDs, which would use 0.18, 183.6 watts of power. And if we divide that by 12 volts, it would take only 15.3 amps. Yeah, 4,440 times 0.18 equals, yes, 800 watts. No, it uses for every color, including white, on maximum. So if you have red at the maximum, it uses 50 milliamps. If you have green at the maximum, it uses 50 milliamps. If you have blue at the maximum, it uses 15 milliamps. If you have yellow, red and green at the max, then it also only uses 15 milliamps. So it's always 15 milliamps. And that's because the LED internally is built up like this. let's make that a little bit larger. So you have your first LED, the second LED, and the third LED all in series, and then these are just PWM'd. And then there's a series resistor. Yeah, 800 watts is a lot. So also what I received today is I talked about last time. I have this wait a second. So I have this 460 watt server power supply, and Julian Elet, shout out to his channel, made a video on these, like they are called ATX something, but these are like little power distribution boards which you can just slide on these proprietary connectors, and the server power supplies only provide 12 volts at crazy amperages. So if I get this back on, it will then make this 12 volts available to 612 ports, where you can plug in the normal graphics cards cables. I don't know if there's a specific name for them. And yeah, and it has a little voltage display in the middle and an LED which just blinks in random colors. So this is pretty interesting. I will probably use this to power the LED tiles once I have more than one, I guess. And this should be able to provide 38.3 amps at 12 volts. So that will be enough to power the maximum supported amount of LEDs for the Nanoleaf clone thingy. So the maximum supported number of tiles theoretically is 254, and then we need to times that by the 18 milliwatts or 180 milliwatts. So this will be 45.72 watts, and if we divide that by 12 volt, then we have, no wait, I miscalculated something. Wait a second. This can't be right. What was I saying? 180 milliwatts. So oh no, I forgot to calculate these. So 254 tiles times 6 LEDs, which is 1524 LEDs, divided by the 180 milliwatts, which gives us 8,466. Once again wrong. So 1,524 times 0.18 milliwatts, or watts, 180 milliwatts, will be 274.32 watts. And then divide that by 12 volts, and that will be 22.8 amps. And that is what this power supply can still provide. So I could control, or I could provide, if we calculate it differently, if we have a maximum of 38.3 amps, so 38.3 amps would be times 12, 459.4 watts. And if we then divide that by the 180 milliwatts, then we get 2,553 LEDs. And then if we divide that by 6 LEDs per tile, we could theoretically control 425 tiles with one of these power supplies. And for the size, that is pretty impressive. But again, servers take a lot of power for calculating stuff. Bolly, so what did you write? 30.3 M times 30.3 amps. No, it's 38.3. Did I say something else? You were so 0.09 amps per triangle equals 1.08 watts per triangle. Yeah, so 425 triangles would be the maximum you could control with this. And then for that you would need 2 controllers to control the triangles. But in order to make that work, my friend and I need to fix the calculation for the colors on the ESP because it's currently too slow for our animation. So we need to optimize or use optimized functions for that. Which will be a fun thing to do. We will also use a fixed point implementation instead of floats, so a fixed point integer instead of floats, because the calculation with that is already faster. Like, I don't want to lean out of the window too much, but like 4 or 5 times quicker. And then also use the 16-bit sine and cosine functions from FastLED, because they are also optimized to be a ton faster. If I look into their code, they claim that sine 16, oh, this is the wrong file, give me 1 second. Trick. So they claim that their sine 16 implementation is the 16-bit approximation is more than 10 times faster than floating point sine and cosine, while the 8-bit approximation is more than 20 times faster. So now we will need to refactor the ESP code to make it all integer arithmetic, and that will hopefully give us the speed we need to control our theoretical max of 254 tiles, but I don't think that that will happen. Why not use lookup tables? Yeah, so the sine 16 implementation of FastLED is already using lookup tables. So they say it's an approximation, and they use a lookup table, sort of. They use a small lookup table and then blend between these values from within the lookup table. Like, I think they have 1, 2, 3, 4, 5, 6, 7, 8. 16, yeah, they have 32 values in their lookup table, and then they use that and blend between those 32 values to give a highly accurate result. So the approximation never varies more than 0.69% from the floating point value you'd get. Yeah, so since we don't want to program it all from scratch again, we will just use the FastLED library, and in combination with that, the CNL library. So the CNL library is the compositional numeric library, and that is a library for fixed precision numeric, or it's a library of fixed precision numeric classes which enhance integers to deliver safe, simpler, cheaper arithmetic types. And in conjunction with that, because FastLED has an implementation for they have an implementation for fixed precision numeric numbers, but it's pretty much crap. Everything else they did, man, that is great stuff, but the template class for their fractional integers, that's what they call it, is bad. It's not only wrongly implemented, because they swapped around the fractional part and the integer part around, but since they're only using the 8.8 integer, which has an 8-bit integer and an 8-bit fraction, they don't even notice that the implementation is wrong. Because for all the other implementations or type definitions for like 12.4 integer or 6.2, it's flipped around. So they are defining a type def for 6.2, but in reality it's a 2.6. So they mixed something up there. But since only the 8.8 integer is used, they never noticed that. But this implementation lacks a lot of stuff. You can't, you don't have arithmetic functions between fractional integers or fixed precision numerics. And that's why we are going to use a specific library for that, which includes it all, because there's some math included, and that way we don't have to reinvent the wheel. So we will just pick the best from FastLED, which are the assembler written, for example, ease in out cubic functions or whatever, which will be pretty fast on the ESP also, and then use the numeric fixed precision classes for the rest. And that will also speed up everything once more. But only tests will show how fast it is. But currently I'm very happy so far. If it will work out, we will be able to drive wait. So if we could maximize or use every single bit of our 1 megabit serial connection, we should be able, and I've shown that multiple times, we should be able to control 83 tiles at 60 FPS, and the 83 is in the full color mode. So Let me show you what I mean by that. So give me 1 second. Oh no, I can't show you. Because I broke the code. But the full color mode in theory is whenever we control each individual LED of every tile to get a higher resolution of animations. And there we can do a max of 83 tiles at 60 FPS, which is the mathematical theoretically maximum. Or if we only do 30 FPS, we can do, we can do 166 tiles, so twice that. And if we do the single color mode, where all 6 LEDs of a tile are set to the exact same color, then we can actually do, theoretically, divided by 60. So at 60 FPS we can already do 333 tiles as a theoretically max. Since our controller can only assign 254 triangle IDs, we will never be able to even get that far to 333. Time for a Google Sheet, yeah, maybe. And if we would even go further than that and use only 30 FPS, we could theoretically control 666 tiles with a single controller. But then we would need to figure out a way to increase the ID of the tile to be not only 1 byte but 2 bytes. But then we lose. Then we have to write 1 byte more per message, so we lose the maximum amount of. So we lose a lot of tiles to be able to control. Because the messages get larger and then we can send less messages due to that. Yeah, so maybe I will cook up a Google Sheet for that. Let's see. At least I will have to write it down somewhere because I'm always recalculating everything. So since I've been already streaming for 2 hours now, I think it's a good time to end the stream right now, because we have talked about the tiles project and we fixed what I wanted to fix during the stream. So I hope everyone was enjoying the stream and learned something. I at least again learned a lot about hot air soldering. And yeah, give the video a like, or the stream, and if you liked it, of course. But if you didn't like it, you can also give it a thumbs up, I guess. And maybe I will stream on Thursday again, but I'm not quite sure about that. It depends on how far I can get with the project until then, and also it will depend on whether the gel PCB PCBs are going to be delivered. So I hope you enjoyed the stream, and you will maybe see me on Thursday again. So have a good evening, or in whatever time zone you are, have a good morning, or a good midday, I guess, or whatever. And have a great time. Bye bye.